I'm Greg, and together with Jojo, we will be presenting our research. My part focuses on perhaps the most widespread noise factor, that is partitioning, and specifically its influence on drag signals. In previous workshops, we've seen many results being submitted with rather large variability, and we asked ourselves how much of this variability is due to the accuracy of the code and its best practices, and how much is simply due to noise factors. We asked ourselves whether we can improve the precision of the data, and why do we observe the different solutions, where those solutions originate, can we mitigate them, and if so, at what cost? We are sure that if we run the exact same file, exact same simulation, we will get exactly the same results, provided a series of requirements is met. Therefore, machine precision of computer is not a sufficient factor, a sufficient explanation for explaining different results for the same physical problem. Only in combination with changes to the computational problem and non-linear nature of Navier-Stokes equations does it lead to change of results. For steady-state research, we already had a presentation during our meetings, so we will just jump to conclusions relevant for the automotive industry. So what we usually see is not proper convergence of the steady state. We usually see undesirable wake, vortex shedding, and oscillatory convergence of forces. How it's usually dealt with is we just averaged fields and forces. So for such not properly converged steady-state signals, we found out that when using coupled solver, CFL number and how the simulation develops, how the CFL number develops, the road to convergence matters for the consistency of obtained results. For transient simulations, we used DVS K-omega-SST on a high Y plus mesh generated inside STAR-CCM plus. We used AutoCFD2 geometry input, which is important as the more recent tessellations addressed some of the problems that we highlight later on. Transient simulations are perhaps trickier to post-process, partially due to initial transients that are difficult to accurately and robustly predict. Algorithmic approach to calculating initial transients is useful. However, small changes such as performing calculations on different number of cores, as we see on this slide, can lead to significantly different initial transient prediction, which we found problematic in studies of noise factors. If we divide drag signal into segments and plot the distribution of drag in each segment, we will arrive at such plot. And in an ideal scenario, we should be able to differentiate between initial transient signal exhibiting higher variability and the rest of the signal. Unfortunately, in reality, that's often not the case. We can see that sudden changes can occur anywhere at the beginning or at the end of the signal, and the question arises which one is physical. An example of such sensitivity can be seen on this signal from Skoda, where over half of 30-second signal was discarded. So for noise factors investigations, we opted for consistency that comes with predefined initial transient duration. For our cases, we settled for 2 seconds. In transient simulations, the errors adds up as time progresses, eventually leading to different signals. On this plot, you can see 2 signals from the same file, just run on different number of cores. And they at first almost perfectly follow each other, then some small differences emerge, and eventually the signals split. These 2 signals not only progress differently in time, but they can also have different statistical properties comparable to effects of small geometry change. We could not make the signals overlap for long periods of time, even if we run with extreme settings for those kinds of applications. We run with double precision, much tighter AMG tolerances, much deeper convergence within time step. This video I'm about to show you shows differences of pressure distribution on the body of the car for the same simulation, just run with different number of cores. We can see that the differences originate first on the rings, and then they emerge independently on some pillars on the bumper and mirrors. These perturbations usually propagate and convect downstream. And maybe what's important, common characteristics of those places is high curvature and perhaps insufficient mesh to properly resolve those regions. I would like to reiterate that if we run the same file with the same submission script, on the same resources, the differences will be 0. Next plot shows results of a study where we run different number of inner iterations with different number of cores. We can see that there's a clear trend when we converge the solution more as is expected from such convergence studies. But what's more interesting, there seems to be also small variability when we converge the solution within time step more. We can see this on this small plot above. It is worth noting that the sample size that we have is too small to draw any convincing conclusions. But going further, we can see the plot that shows three pairs of post-process signals. We have dark green for 5 inner iterations, light green for 8, and red for 12 inner iterations. The signals are basically averages from the tail. So what this means is that the first samples on the left side are representative of the most recent samples. Consequently, the samples on the right take into account most of the signal, and the last values are averages of the whole signal. Analyzing it, so what we should really be looking at is the area in the middle, preferably to the right side, have the most samples for statistical relevance. And because of the initial transient that is inside this part of the plot. We can see that more converged signals seem to give more consistent results, both in respect to absolute values as to how the signals develop. We did the same study for the deflector case with 5 and 8 inner iterations, varying number of cores, and the observations seem to be the same. Better converged signals have smaller spread between them. On the next plot, we see two pairs of signals, one for baseline case, one for deflector case. We see that the effect of partitions for the baseline case is lower drag, but for the deflector case, it's higher drag. So running on the same resources, we are comparing between those pairs of signals. For the 8 inner iterations, it's slightly different because more partitions lead in both cases to higher drag. So the conclusion that we have is that there's no clear direction in the impact of noise factors as it's expected from random errors. What are the key takeaways from our research? One is that obtaining ideally overlapping signals for different computational problems might not be possible. Regions of relatively low mesh resolutions were identified as places of origin of differences. If we converge the time steps better, drag force signals seem to be more similar, potentially limiting impact of noise factors. And errors do not follow a set pattern. When we compare deltas, the errors can add up or cancel out. As for the questions, open questions, we are aware that our sample size is small, so we are curious whether our larger sample size would confirm our findings. And the holy grail, where lies the balance between time step size, time step convergence, and number of time steps to get the most consistency and accuracy. With that, I leave the floor to my colleague, Giorgio.
Thanks, Greg. Okay. Please allow me to shamelessly change the topic just for 3 slides, and then I'll touch back on the noise factors at the end. But it's just an update of what model it is results. So for a big company, there's lots of people working on this, and just want to present this, an update. So I took the latest version of our code, so the one that's going to be available next month, and I use the same mesh as previous workshop, and we're just going to take a look at the results very quickly and at the performance. So first, the settings, usual ones. Just go on. Implicit time stepping, PDF2 formula, and using the whale model. The total duration time is 4 seconds, but we throw away the first second, so we're averaging over the last 3. So hopefully this keeps the Skoda guys happy. I see a note at the end. That's really good. In this particular case, I'm restarting from runs. The solver, third order scheme in space, and simple C for pressure velocity counting. And I'm using the slight variation of PDF2. This one has more than 2 time levels, so it has a lower absolute error, but it's still second order error. Delta T is 1 10 to the minus 4, and the delta drag, that's the main results I'm going to show you, is 9 drag counts against 12 of the experiments. Now, local solution, velocity profiles. I picked the ones that I think are most representative. L1, something on the body, looks pretty good. And then the lower part, we have U3, U5. So all the trends correctly captured, but we're happy with that. The areas where I think we need to look at are like this one. So the weight deficit, we're still missing a little bit there, but judging by the results that I've seen yesterday, I think we need just a little bit more mesh resolution. And the other areas is, again, B5 here, there's something to work on, but you've seen it yesterday, lots of people getting these results. Now, in terms of performance, we always told you that to run this case, we needed 24 hours. Now we need 20, so the code got a little bit faster. I think the results are better, so that's good news. And it's also, for me, encouraging to see how the new, in this case, NVIDIA generations of cards pretty much give us a factor of 2 every time they come out. So the laziness in me thinks good that the solver is fine. We just need a better hardware. But no, so that's the good news. So roughly 20 hours for 16 V100s. Roughly the same time if you use 8 A100s, and roughly the same time if you use 4 H200. These are the very latest one. It also means that if you double any of these, in this particular case, I use 8 H200, you will get your results in overnight, so a little bit more than 10 hours, 11 hours. Again, these are the latest results, mixed precision for 4 seconds of physical time. I forgot to say 5 binary iterations if you want to make comparisons. And what else? These 3 cases, so these I've run just for, let's say, scalability test, but I've run myself all these 3 for both configurations, and I always got the same 9 run counts. So it looks like, which also the Scotty guys have seen, one model LES is less sensitive to noise factors. And that was my hook to noise factors. Thank you very much.
Thank you. Yeah, but in interest of